All right, finished my general announcements. Some of the highlights are students should have picked up 3 different handouts today. One is due on the 25th. The other is due on the day of the Chapter 3 test, projected to be on October 30th. Okay, if you weren't here for the test last class, you have 2 days to make that up. The same would be said for the homework that was due yesterday, the review packet, the Chapter 2 review work, as well as the Frappy worksheet, which was an option to turn in. Okay, students were already given time to complete the first problem, 3.11, which is certainly not a Chapter 3 topic, but we're going to move right into Chapter 3. Let me give you a very brief overview of the course so far, though. In Chapter 1, we kind of jumped around a little bit. We looked at categorical displays. We looked at pie charts, segmented bar graphs, and then we moved to, what if the data is not categorical? What if it's quantitative? And we looked at stem plots and dot plots and histograms and box plots. Okay, so we looked at a bunch of quantitative displays. Now, while we did look for associations between categorical variables, okay, for example, the Titanic, you had data with 2 categorical variables. What was your class? Okay, and did you survive? Okay, you were either dead or alive. Those were the possible settings for survival. You were either first, second, third, or crew. Those were the possible settings for class. And we looked for an association between those categorical variables. We looked for a relationship between those categorical variables. Chapter 3 is, let's look for an association, actually we call it a correlation, between quantitative variables. Chapter 3 is all about, let's build a scatter plot. We don't have 2 categorical variables, we have 2 quantitative variables. A really simple one that I could throw at you that I'm sure you all could hold in your heads is that if you look at all people and you use the quantitative variables height and weight, you'd probably see a positive relationship, because in general, the taller you are, the heavier you are. Obviously, there are exceptions to that rule. Okay, you can find plenty of people that are taller than me that are lighter than me. You can find plenty of people that are shorter than me that are heavier than me. There are going to be exceptions to that overall pattern, but the general pattern, if you looked at all points as a big cloud on a scatter plot, is most of them fall along a positive trend line. Does that make sense? Okay, so that's what Chapter 3 is about. Now, when we were describing histograms, we learned a whole bunch of terminology. Okay, if you wanted to talk about shape, you said things like skewed left, skewed right, or uniform, or symmetric. If you wanted to talk about center or spread, unusual features, there were a lot of key buzzwords you would throw out there. I now want to teach you the key buzzwords you're going to use in a scatter plot. And the first one we're going to look at, if you tried to use the histogram terms to describe this, you might say it's unimodal and symmetric. Please don't say that. This is not a histogram. It's a scatter plot. So don't look at this and call it unimodal and symmetric. It's not. Okay, it's not even close to those terms, because those terms are reserved for histograms, for one variable quantitative data. And you take the one variable and you break it down by bins, and then you look for the patterns. This is 2 variable data, or bivariate data. So when we want to describe a scatter plot, we use, instead of shape, center, and spread, okay, we use terms like direction, form, strength. We still want to talk about unusual features. So we're still going to talk about outliers. We'll eventually get to a more technical term for outliers, which is influential points. Okay, so that's what we mean when we talk about unusual features. When we say direction, what we're looking for is words like positive, negative, increase, decrease. Okay, and we always talk about the patterns we see as a general tendency. So going back to the height versus weight, you would say as height increases, weight tends to increase. Don't get overly attached to that word. Use whatever non-deterministic word you want. You know, as height increases, weight generally increases. I don't really care how you want to say it. Okay, but you cannot say definitively. You can't say taller people are heavier. Wrong. Okay, that's just a general pattern that a lot of people fall into. Okay, for form, most of what we look at in this entire chapter is going to be linear. We will look at some curved data, some parabolic, some exponential stuff, but pretty much every time we run into those curved models, we're basically going to say, oh, look, I can't fit a line, it's curved. You know, or if I did fit a line, in what ways would that cause me to make errors? Okay, and generally speaking, for curves, if you try to fit a line to a curve, what that means is in some areas you're overestimating the truth, and in other areas you're underestimating the truth, and that happens in a very patterned fashion. For example, because I can see some of you looking at me quizzically, if I tried to fit a line to this data, and let's say I thought the line looked like that, I should do this in red, it's completely ridiculous. Okay, let's say I try to fit a line. And we haven't gotten to this graph yet, but it's basically showing the speed of travel versus fuel efficiency. Well, if you're going this fast, I think your fuel efficiency is somewhere in here. So in that entire region, I am underestimating the true fuel efficiency because the true fuel efficiency is up here somewhere. Does that make sense? And then later, because the curve starts to go back down, if you're traveling 100 miles an hour or faster, my line thinks your fuel efficiency is somewhere up here. It's clearly overestimating the truth because the truth is down there somewhere. Does that make sense? So that's sort of as far as we'll take curves. We'll say, oh, look, it's curved. It's not really appropriate to fit a line to it. And by the way, here's why. And we'll talk about the problems that might create. Okay. And then finally, strength. I do not expect these words to make sense yet, but by the end of the period, they should. Okay. Totally random, which is there's no correlation at all. But then we're going to use words like weak, moderate, and strong. Perfect is sort of an unrealistic situation. It really doesn't ever happen with raw data that you collect. And in most cases, perfect correlations only occur with unit transforms, meaning if you graph how tall are you in inches and how tall are you in height, okay, or in feet, excuse me. You know, how tall are you in inches? How tall are you in feet? Well, that's a direct unit conversion. You know, if you're 60 inches tall, I know you're exactly 5 feet tall. So that is a perfect relationship, but that's not really data you would collect. Okay, so I don't expect these terms to make sense yet. It's kind of like I'm throwing everything at you but the kitchen sink on day one, but we'll get used to using these terms as we move forward. Okay, go ahead and turn the page. So here's an example of described associations. The idea is if I'm standing behind the board and I can't see what's on the screen, what do you see for that? Histogram. When you're looking at a histogram, it's sort of like, well, if I couldn't see it, how are you going to describe it to me so I can get a rough image of what it looks like? And that's why you use words like it's unimodal, centered around this number, but you know it's skewed right because it spans from here to there, you know, or whatever, however you're going to describe it. Okay. Now, by the way, while this is an exaggeration, it's an oversimplification of the truth. This is a reflection of reality for people who maybe don't know it. Okay. What this is again showing is the speed of travel versus your fuel efficiency. How many miles are you able to travel per gallon? Okay. And this is actually the truth for most cars out there. Okay. Most commercially designed cars for just anybody who wants to buy a car. If you're driving really, really slow, you're not going to get very good fuel efficiency because you're literally not going. But as you go faster and faster and faster, and usually approaching somewhere around highway speeds, that's usually about the point that the car reaches its optimal fuel efficiency. You know, in car commercials nowadays, they report both city and highway mileage. You know what I'm talking about? They didn't do that before. When I was a kid, they just reported one number. It gets 27 miles to an gallon. And then people would buy the car and be driving in the city and be pissed that the car's brand new and I'm only getting 9 gallons per mile. And then they sort of instituted this policy of, okay, car manufacturers need to report 2 different numbers. What does the car get while you're driving in the city where you're coming to a stop and going and stop and go and stop and go and you're driving at lower speeds? What's the average in that region? And what's the average at highway speeds? Does that make sense? Because one is usually lower than the other. Now, as you go faster and faster and faster, friction, wind resistance, you know, the mechanical imperfections of the car start to kick in and you start to lose fuel efficiency. Okay, so this is, again, it's an oversimplification of reality, but it is kind of the truth. You get not so good fuel efficiency at very low and very high speeds, and the sweet spot is somewhere in the middle. Okay, so if I ask you to describe this, here's what you might say. I'm going to give you a chance to copy that, and then I'm going to break down the parts. It occurred to me to add something to the board so you can understand from a grading perspective what's going on in my head if a student writes this. When you're describing a scatter plot, I am looking for, this is sort of how back with the histograms we talked about SOCs, you know, shape, outlier, center, spread. This is that scatter plots, form, direction, strength, unusual features, and don't always include context. So the moment I see the word curved, you've got credit for form. Like you've made it clear it's not linear, it's something else. Okay. When you talk about direction, okay, well, to be the tends to increase and tends to decrease thing. Okay. Now for strength, that's going to be this word right here. It's strong. I don't expect that word to make sense to us yet. I have to explain to you why would you use the word weak or moderate or strong. We'll get there. Okay, that's actually going to be the main focus of today. Okay, I'm going to try to keep things a little simple after this. Now, for context, it's a little weird. Okay, when you talk about context, that's talking about the relationship of the variables. As gas mileage goes, well, it's kind of like this whole sentence. Okay, describing in words what your direction means. Okay, context is what do you mean by those words? Okay, so when you say, well, this thing, your gas mileage, your fuel efficiency seems to go up for speeds 0 to 55, okay, but then your fuel efficiency seems to go down for speeds above that, that's what context is. Okay, so it's not just using words like fuel efficiency and speed. It's actually explaining to me, what do you mean when you say, well, this goes up and this goes down? Okay, like give me a little bit more. For example, with the whole height versus weight graph, if you just say, well, there's a strong relationship between height and weight, you've gotten strength, assuming there is a strong relationship, but simply using the words height and weight is not going to get you context anymore. Okay, if you say there's a strong positive relationship between height and weight, well, again, what do you mean by positive? You have to say, as height goes up, weight tends to go up. That's your context. Explain to me in words what the increase or decrease or positive or negative means. Okay, I thought I saw a hand. All right, so the rest of the day, we're basically just going to laser focus on strength. Weak, moderate, strong. What does correlation actually measure? Because it's a number we're going to be using. Okay, so a few ground rules for association and correlation coefficients. Before you even try, it says fill in the blanks regarding the conditions for applying the correlation coefficient R. So if you ever see me use the lowercase letter R in the class for the rest of the year, ever see me use the lowercase n in this class, ever, I'm talking about sample size. Okay, so the first thing you have to ask yourself is, do you even have quantitative variables? Because if you don't have quantitative variables, you shouldn't even be trying to build a scatter plot. If you have two variables and they're categorical, well, then you should build like a table, kind of like what we saw with the Titanic data. Okay, but if you have two variables and they're quantitative, fine, build a scatter plot. Now, you're going to ask yourself, is the scatter plot straight enough? Now, what we really mean by that is, when you look at the data, do you see an obvious bend? If you don't see an obvious bend, then just go with it and call it linear enough. We're going to see an example of that in a moment. Now, are there any outliers? In general, if there are outliers, especially if there are influential points, and that's something we'll get into much later on, what you might do is go ahead and find the correlation with all of the points, but then say, you know what, there's this one point over here that really doesn't seem to belong, or there's this one influential point over there that clearly doesn't belong. Let me remove those and then recalculate correlation for the remaining data. That way I can talk about what is the relationship in general minus this one point over here that's kind of screwing things up. Okay. Now, what does the correlation coefficient R do or say? It measures the strength of a linear relationship of two variables. I still don't expect you to know what that means yet. Let me get there. Strength is synonymous with compactness. How compact are the points along the line or the curve or whatever? Okay. Now, association is a term which applies a pattern or relationship exists. Okay. The thing is, if you say association, that just in general means a pattern or relationship exists. And I don't care what kind of variables you're talking about, quantitative or categorical. But for anyone who knows about the term correlation, anyone who's been educated on the proper use of that term, the moment you say correlation, you have to be talking about quantitative variables. It's a quantitative term. I'll give you a great example. And this was something I didn't, ding anybody for, because there's no way you could have known. When we did our first free response challenge of the year, and you all were analyzing the application of the death penalty in Philadelphia in like the 1970s, a number of you said there is a correlation between the race of the defendant and the use of the death penalty. That was a misappropriation of that term. You should not have been saying correlation because you weren't analyzing quantitative variables. You were looking at categorical data. So what you should have said was there's an association between the application of the death penalty and the race of the defendant. That was not something I penalized you all for because there's no way you could have known that at that time. Okay, now to be clear, just because you see a pattern, that does not mean you have causation. This is a huge thing that gets wrong that is done wrong in the world around us, including in news and media and just all over the place. People see patterns and they think they can extract cause from seeing that pattern. And nothing could be further from the truth. Just because you notice a pattern in the world, that does not mean you have any idea why that pattern is existing. Okay? And I believe me when I tell you, I can show you things where you would think, oh yeah, clearly those two things are related. But there could easily be something in the background that's creating the correlation. It has nothing to do with X causing Y. Okay? That'll be a huge thing that we get into later in this unit as well. Just understanding, and we're going to get into our experimental design unit, and we'll kind of revisit that idea that just because you see a scatter plot with a pattern, that doesn't mean there's a relationship. Okay. In fact, all right, now I don't know if it's a good idea to get this much of an aside, but there's actually a gentleman, I forget his name. He literally committed himself to building a website to investigate what he calls spurious correlations. He wanted to prove that just because you see a pattern, it doesn't mean there's a relationship. Okay. And so he went out of his way to scour the earth for data of variables that moved in the same direction coincidentally. And it's actually a lot easier than it sounds. Okay. In fact, I'm wondering if I have one of those prepared. Oh, I don't. It's going to be later. Okay. I'll wait until tomorrow. I really wanted to show it now, but I'm pretty sure it comes up tomorrow. All right. Go ahead and turn the page. Okay. This is where we're going to try to practice some of these terms. So 3.15, identifying strength, direction of associations, check all that apply. I'll zoom in a little bit more just so this is a bit easier to see. So when I look at this, clearly it's not linear. Okay. Clearly it is curved. Okay, so I cannot check that bottom check mark. It's not a linear association. However, if you see the curve that kind of follows the points, I think we can all agree those points do a really good job of following that curve. So the only thing I'm going to check here is strong. That's the only thing I would say for certain. If you actually take the time and draw a curve that kind of follows along these points, those points do a fantastic job of following that curve. So I would argue they are fairly compact along that model. Now, in terms of whether you don't want to call it positive or negative, you can either leave them blank or you can check both. I really don't care. But if you were describing this, you would need to talk about both. You'd have to say, well, in this region, as this thing goes up, this other thing tends to go up. But in this other region, as this thing continues to go up, this other thing tends to go down. You would kind of have to talk about both. Now, with the next one, with B, again, you could clearly fit a line to that, and clearly, as X goes up, Y also goes up. So this is a positive relationship. And I would argue, however, that it is not strong because those points are not super compact along the line. Okay, so I would say, all right, I can clearly see the pattern, but the points aren't super compact. I'm going to call it moderate. Now, right now, this probably feels super subjective, but we will put a definition on when do you call it weak, when do you call it moderate, when do you call it objective thing, the visual, like I'm going to guess at it type thing. Okay. Now, before I keep going, one other thing I want to make clear. When you are describing something as positive, please understand I am not calling this positive because as X goes up, Y goes up. I'm calling it positive because the variables move in the same direction. That's what a positive correlation means. Because check this out. You can look at these points and say, well, if you're taller, you're probably heavier. So as your height goes up, your weight probably goes up. They both go up. Or you can focus on these people and you can say, well, if you're shorter, you're probably not as heavy. Notice both variables are going down together. Does that make sense? So do not tell me it's positive because both variables are going up. No, it's positive because the variables move together. They can both go up or they can both go down. That is a positive relationship. Now, if that doesn't make total sense, let's look at the next one. It has a negative relationship. If you focus on this end, of the data, what you're noticing is for higher values of x, the y value tends to be lower. So as one goes up, the other goes down. That's a negative relationship. And if you focus on it in the other direction, well, for smaller values of x, so as x gets smaller, you typically see larger values of y. So as x goes down, y goes up. Notice they're moving in opposite directions. So a positive relationship means variables that move together. A negative relationship means variables that move in opposite directions. Okay, that's what it means. And I say that because the kids that describe, the reason I know it's a negative relationship is because everything's going down. Correction, if everything's going down, it's a positive relationship. Do you hear what I'm trying to point out here? Okay, so some kids will say it's a negative relationship because everything's going down, but you've literally just described a positive relationship, because if the variables are going down together, that's a positive relationship, because the implication is they also go up together. Okay, all right, let me get rid of all that craziness. So C, if it wasn't already clear, is strong, linear, and negative. Those are the three things that you should be checking off for C: strong, linear, and negative. Make sure I bring these check marks back in. There we go. All right, and then for D, let me zoom out because it's not really showing the way I wanted it to. Perfect. This is a situation where some people might not be comfortable describing it as linear. But this is why I said the terminology is linear enough. Like when you look at this data, do you see an obvious curve? I don't. Okay, when I look at this, I don't see like an obvious curve one way or the other. So to me, a line does a decent enough job of following those points. But of course, they're not compact at all. So even though it's a negative linear relationship, it's weak because the points are not at all compact along that line. All right. Let's see if you all understand just the concept of strength, okay? And try to complete 3.16 yourselves. It says determine strength visually. List these scatter plots in order, strongest to weakest. Okay, I'm going to wait 2 minutes here. All right, so which scatter plot shows the strongest relationship? F. Okay, and then I kind of cheated. I did this in a visual system. If you start at F and just rotate counterclockwise, you'll get the answers. F, C, B, A, D, E. That is the order I was looking for. Okay. And again, strength is how compact are the points along whatever model it is that would predict them. Okay. And in this case, I only stuck with linear models. So line does a fantastic job. Line does a really good job. Line does a decent job. All right, I can see it, but it's starting to get spread out. I can still see it, but it's really getting spread out. And then E is just like a big cloud of nothingness. Okay, there's no relationship in E. Okay, questions? Okay, now here's where we're going to get away from the subjectivity. I said before that I'm going to teach you a number system so that when I give you a correlation coefficient, you will know whether or not to describe it as weak, moderate, or strong. Okay, so first of all, if there is no relationship, I don't want you to have to look at a picture and decide, well, is that nothing or is there a line there? So if correlation is anything weaker than 0.5, and notice I put absolute value bars, that's on purpose. I'm telling you the magnitude of R is less than 0.5 because R, okay, if it's a positive correlation, well, then R is positive. If it's a negative correlation, well, then R is negative. Okay, but if R is anywhere from 0 to 0.5, the correlation there is so weak that you basically say there's nothing really worth mentioning going on. Now, once you cross 0.5, you've now entered, okay, there is something there. But if R doesn't get to as big as 0.7, notice I'm including 0.5, I'm not including 0.7. So if you're like 0.54, that's weak. If you're 0.68, that's weak. If you're 0.6912734, that's weak. The moment you hit 0.7, whether it's positive or negative, now we're going to call it moderate. So if I tell you the correlation of this data between height and weight is 0.72, it's moderate. So if you cross 0.7, you're now in the realm of moderate. Notice I included 0.7 here. I did not include 0.9 with moderate. So if you're 0.8999999, you're still moderate. But the moment you hit 0.9, we call you strong. And anything other than 1 is strong. If you actually get a correlation of exactly 1, then fine. It's a perfect correlation. But as I said already, you in the real world, when you're collecting real live data, you basically would never see a perfect correlation. Because the only way you get a perfect correlation is if you can draw a line that hits every single point. Okay, and that basically never happens. Even if one point is a little bit off the line, that's going to weaken the correlation to like 0.99999 something. What's up? All right, go ahead and turn the page. And let's put it to the test. This one I am going to give you 2 minutes because I'm assuming there's going to be a little bit of a debate about these. This is a match game. You're using each number exactly once and match it to the graph based on the correlation provided. Go. So before I just reveal the answer key, let me make it clear that one thing that I think is going to help you with this type of thing is decide if I fit a model to it, what is that model doing? Here, clearly that model would be going down. So that one has to have a negative correlation. Here, if you try to fit a line to it, which wouldn't really be appropriate, clearly that line would be going up. This one, the line would clearly be going down. So by process of elimination, what does the correlation of C have to be given the options? Say it again. Which one? No, of these options. Your options are 0, negative 0.5, 0.5, and negative 0.98. Wouldn't be 0.5. The first one has to be negative. The second one has to be positive. And the third one has to be negative. Which option is still left? 0. This is C. The reason for that is because correlation is supposed to report to you, do the variables have a positive or a negative relationship? And in C, they have both. There's a certain range where as X goes up, Y tends to go up. But then there's a separate situation where as X continues to go up, Y tends to go down. If you tried to force yourself to fit a line to C, it would be a flat horizontal line. It wouldn't be going up or down. Its correlation would basically be 0. I think if you figure that out, it kind of helps all the other ones click in place. I would argue the most obvious one is 4 because it's very, very tightly packed points and they're going down. So it's a value that should be close to 1, but it should be close to -1 because it's a correlation, because it's a negative relationship. Okay, so I'm looking for CABD. Okay, and what I wrote here is just sort of a separate explanation of B and C, that they each have their own reasons for not being in that 0.7. I would argue both B and C are moderate relationships, but remember, correlation is meant to measure the strength of a linear relationship. So even though, like if you actually found a curved model, I would agree that's a 0.7. That's probably a 0.7. Okay, because those points do a decent job of following the model. But if you try to fit a line to it, the line's not going to do a great job. Okay, so here's sort of the recap of everything I wanted you to understand from today. This is the summary here. Number 1, understand that correlation is a number that is strict between -1 and 1. You will never see a correlation of -2.37 or +1. Correlation can't go outside the boundaries of -1 and 1. -1 is a perfect negative relationship. 1 is a perfect positive relationship. 0 is a meaningless cloud of points that have absolutely no relationship whatsoever. Okay? R defines strength of correlation, in other words, how compact it is. So for example, watch this, watch the screen. Those points are very tightly packed along a line. If I rotate this, have I changed how compact the points are along that line? No. So the correlation stays 0.99. If I do this, it stays 0.99. I don't care how you rotate these points. If they're still in a positive relationship where they're going up together or down together, correlation's 0.99. If I flip it to now make it so that they're going in opposite directions, as X goes up, Y goes down, or as X goes down, Y goes up, well, then it's still 0.99. It's just negative. Okay? And I don't care if it's a moderate relationship. No matter what you do with these points, as long as you keep them kind of going up, the correlation is going to stay 0.7. R gives the sign of the slope, not the value. So understand, I don't know if the slope is going to be 1/10 because it's barely going up, or if the slope is going to be +7 because it's rocketing up. I cannot extract that from correlation. You cannot know what the slope actual number is from correlation. R is for linear data. So if it's ever nonlinear, that will kind of mess with the correlation coefficient. And nonlinear associations weaken it. That's actually what I just said a moment ago. Okay? So hopefully you walk out of the room with some better idea of correlation, but we'll practice it more tomorrow. At this point, we're done. Thanks for watching. Have a good one.